Imagine a world where the temperature swings 600 degrees between day and night, where winds scream across barren rock at hundreds of kilometers per hour, carrying no moisture because there is no water left to carry, where the atmosphere itself was stolen, molecule by molecule, leaving behind a surface exposed to radiation that would sterilize anything we recognize as life. This is not a hypothetical disaster scenario. This is Venus, and the story of how Earth's twin became the solar system's most extreme weather laboratory begins with a question we still cannot fully answer. What turned a world that might once have been habitable into a runaway greenhouse hell? Venus orbits the Sun at a distance of 108 million kilometers, just 30% closer than Earth. It is almost identical in size and mass, with a diameter only 5% smaller and gravity 90% as strong. For decades, astronomers called it Earth's twin, imagining tropical forests beneath those bright clouds. But every assumption collapsed when instruments finally penetrated the veil. The surface temperature reaches 470 degrees Celsius, hot enough to melt lead. The atmospheric pressure at ground level is 92 times Earth's, equivalent to being a kilometer underwater. And those beautiful clouds are not water vapor. They are concentrated sulfuric acid. The first hint of Venus's true nature came from Earth-based radio observations in the 1950s, which detected microwave emissions consistent with extreme surface heat. When the Soviet Venera probes descended through the atmosphere in the 1960s and 70s, they measured conditions that destroyed most landers within an hour. Venera 13 survived long enough to return color images from the surface, a landscape of fractured basalt slabs beneath an orange sky. NASA's Magellan orbiter, mapping Venus with radar from 1990 to 1994, revealed a world resurfaced by volcanism within the last few 100 million years. No plate tectonics, no magnetic field, no water cycle, just heat and pressure and chemistry operating at scales Earth never experiences. Scientists expected Venus to be warmer than Earth, but not this warm. The runaway greenhouse effect that dominates Venus should have been self-limiting. As temperatures rose, any water vapor in the atmosphere would have been broken apart by ultraviolet radiation, with hydrogen escaping to space. Carbon dioxide, outgassed by volcanoes, should have been absorbed by surface minerals through weathering reactions. On Earth, this carbon cycle regulates temperature over geological time. On Venus, it failed. Instead, carbon dioxide accumulated to create an atmosphere 96% composed of a gas that traps infrared radiation with brutal efficiency. The mechanism that stabilizes Earth's climate became Venus's executioner. The weather patterns that result are unlike anything in our terrestrial experience. At the cloud tops, 60 kilometers above the surface, temperatures drop to -40 degrees Celsius, and winds race around the planet at 350 kilometers per hour, circling Venus in just 4 Earth days, even though the planet itself rotates only once every 243 days. This superrotation remains one of planetary science's enduring puzzles. Atmospheric models struggle to generate and sustain winds that fast without an obvious energy source. The leading hypothesis involves the transport of angular momentum by atmospheric waves, but observations from the European Space Agency's Venus Express mission and Japan's Akatsuki orbiter have revealed structures and variability that challenge simple explanations. The clouds themselves organize into patterns that shift and dissolve on timescales of days. Ultraviolet images show a dark Y-shaped feature that rotates with the super-rotating winds, formed by an unknown ultraviolet absorber that concentrates at certain altitudes. Spectroscopic analysis has ruled out sulfur compounds and simple organic molecules. The absorber's identity remains unconfirmed. Below the clouds, in the middle atmosphere, convection cells driven by heat rising from the surface generate turbulence and eddies. But the dense atmosphere damps out the kind of large-scale storm systems that dominate Earth's weather. There are no hurricanes on Venus. The energy is there, but the physics distributes it differently. The temperature gradient from surface to cloud tops creates a vertical structure unlike any other planet. Near the surface, the air is so dense that it behaves almost like a liquid. Objects falling through it would drift slowly, cushioned by viscous drag. The pressure is sufficient to make carbon dioxide exhibit supercritical behavior, where the distinction between gas and liquid blurs. This creates unusual thermodynamic conditions that affect how heat moves through the lower atmosphere. Convection operates, but slowly, constrained by the immense weight of the overlying air. The central mystery is not what Venus is now, but what it was. Isotopic measurements of the trace water vapor remaining in Venus's atmosphere show a deuterium-to-hydrogen ratio more than 100 times higher than Earth's. This is the signature of preferential hydrogen loss. Lighter hydrogen atoms escape to space faster than heavier deuterium, leaving the residue enriched. The calculation suggests Venus once had water, possibly enough for a shallow ocean. Computer models of the early solar system indicate that Venus might have been habitable for its first 2 billion years, before the sun's increasing luminosity pushed surface temperatures past a critical threshold. Once water vapor began accumulating in the atmosphere as a greenhouse gas, a feedback loop ignited. More warming released more water vapor, which caused more warming until the oceans boiled away and ultraviolet light finished the job. But the timeline and mechanisms are still debated. Some models suggest the transition happened rapidly, within a few 100 million years. Others allow for a slower decline, with transient habitable conditions persisting longer. The surface has been so thoroughly erased by volcanic resurfacing that no geological record survives to test these scenarios directly. And there is a darker possibility, that Venus never had a temperate phase at all. If the planet formed hot and stayed hot, the deuterium enrichment might reflect primordial water delivered by comets, never condensed into oceans. The evidence is consistent with both narratives. What we do know is that Venus's current state represents an equilibrium, however extreme. The greenhouse effect has saturated. Carbon dioxide continues to cycle between atmosphere and surface through volcanic outgassing and chemical reactions with rock. But the system has reached a balance at these infernal conditions. Lightning discharges in the clouds, detected by radio emissions and optical flashes, suggest active chemistry in the sulfuric acid layers. Thunder on a world with no rain. Volcanic activity, inferred from transient increases in sulfur dioxide concentrations, continues to reshape the surface and replenish atmospheric chemistry. The planet is not dead. It has simply found a different mode of operation than anything Earth experiences. The atmospheric circulation itself creates distinct climate zones despite the uniform heat. The equatorial regions experience relatively calm conditions compared to mid-latitudes, where the super-rotating winds achieve their maximum velocity. Polar regions develop unusual vortex structures, massive cyclone-like features that persist for years, driven by dynamics that differ from Earth's polar vortices. These structures churn at the convergence points where high-altitude winds descend, creating regions of enhanced cloud activity and complex chemical interactions. The poles are the only places on Venus where the atmospheric circulation produces anything resembling stationary weather features. The best chance to resolve the habitability question comes from missions capable of analyzing the surface mineralogy and atmospheric chemistry in detail. NASA's VERITAS and DAVINCI missions, along with the European Space Agency's EnVision orbiter, are designed to measure isotopic ratios, map mineralogical composition, and search for geological evidence of past water. If Venus once had oceans, certain hydrated minerals should still exist in rocks protected from resurfacing. If the atmosphere's noble gas abundances match predictions for a wet early history, that would strengthen the runaway greenhouse hypothesis. If they do not, we may need to reconsider the twin planet assumption entirely. The stakes extend beyond Venus itself. Understanding how a planet transitions from potentially habitable to definitively sterile informs the search for life elsewhere. Exoplanet surveys have identified hundreds of worlds in their star's habitable zone, where liquid water could theoretically exist on the surface. But proximity to a star is not destiny. Venus proves that greenhouse feedbacks can override distance, that atmospheric evolution can trap a world in a state we would never have predicted from initial conditions alone. Some of these exoplanets may be Venus analogs rather than Earth analogs, their surfaces already locked into runaway conditions we cannot yet observe directly. The question is not whether extreme weather exists in space. It is whether the mechanisms that made Venus impossible are rare exceptions or common outcomes, waiting in the data from worlds we have not yet studied closely enough to know the difference. Every measurement of Venus refines our understanding of planetary boundaries, the thresholds beyond which temperate climates cannot exist, and every refinement narrows the range of conditions we should expect when searching for habitable worlds around other stars. Venus is not just a cautionary tale, it is a laboratory where we can observe, in exquisite and terrible detail, what happens when the systems that make a planet livable fail completely and irreversibly. The most extreme weather in space is not the weather we fear. It is the weather that ends all weather as we understand it, leaving only heat and chemistry, and winds that blow across a surface no living thing will ever walk.